So this is a continuation of our Category 1 Venting Basics discussion. And I'd like to start out and go through some of the questions. I guess if you want to simultaneously view the video and then also do the questions on the mechanical draft vent basics, you certainly can, or natural draft vent basics. So let's get started. All right, so first thing that I would like to address on here is the fact that moisture is in a vent system is a real problem, and it's something that we have to contend with. It's really our number one issue in any types of new vent systems that are not vented with PVC or any of the types of applications like that. So anything Category 1 primarily is what we'll be talking about in this system. So how do we get it to stop from happening? So I think to some extent we probably need to make sure we can get that flue gas temp high enough. And again, it's a little bit of a problem because the higher I make the flue gas temp to prevent from the moisture from forming, the less the efficiency is out of my appliance. So it's a legitimate issue, but it is what I have to kind of contend with. So that means that if I want to get my flue gas temps lower to get more efficiency, my vent system had better be almost perfect. So exactly what causes the condensation to occur in a system? Well, the first thing is too low of a temp on the vents. So your vent temps, if they get low, and I'm specifically talking about the temperatures of the actual vent system, is going to be an issue on there. You might have too large of pipes, or maybe you've got excessive heat loss in your vent system. That would be another one. Maybe you just didn't use the right materials. If you've got an application that is, hey, you know, this one you should have used an insulated duct or an insulated vent pipe. Maybe it's exposed to conditions it's not designed for. You know, those things can also be a problem with it, and you have to watch those things. So. All right, so what are some of the things that would obviously be ruined by condensation from a vent system? Let's take a look at some of these. So the first one I wanted to show you is the brick and mortar. Now, on the image down to the left here, I want to point this out. You'll notice a lot of the mortar and the bricks that hold the chimney together are really, really deteriorated. That is something that actually happens quite frequently. Now what happens is, and I'm going to kind of point it out here because you don't see it so much on the picture on the left, but they're inside here, this little piece right there, that's kind of like an orangish color, that's actually the liner. Now they can make those chimney liners as either in like a terracotta type of a product, a clay product, or they can even do it as a metal liner. But those are put in there with, you know, generally as like 2-foot long pieces. And so those systems, what'll happen is they'll use mortar in between those pieces. When those things start to leak out, all of a sudden the moisture will start to leak out of those, and then they actually will create a problem where they'll just deteriorate and erode this entire vent system. As you can see, this one's really in bad shape, but that is a legitimate issue. The vent pipes, your vent connectors, all that can become damaged. On the vent pipe that you see here, you can see how water has run back down. What do? I mean, it's one of those where you got to pick maybe something that's a more insulated vent system, or maybe you have to have a T somewhere. You got to design the system so that you don't have that problem where it's running back into the appliance. And then what's even worse yet, if you look down on the bottom here, you can really see how the water has run right back through, and it's going to eat away eventually at the furnace and the controls and create a real legitimate issue. On the picture that you'll notice on the far right here, you'll also see there's an excessive amount of condensation that's been occurring. The cover's not off in front of that furnace, but that's a little bit of a problem. The water runs back, it's acidic, it's going to be a problem. And then of course, if it runs back inside the furnace, you can start to really have problems where the heat exchangers will completely rust out. And that's going to be a real, without going further than that, it's going to be an issue. So a little bit of a problem. All right, so let's take a look at this next one. So on the next slide, what we're going to take a look at is our flue gas dew points relative to excess air. Now the first thing that I want to hit up on is your flue gas dew points should always be less than or equal to the flue gas temps. And that's going to be somewhat relative to the excess air. So if you're, if you were, let's say, running 50% excess air and you were dealing with a mid-efficiency appliance, you'd probably be dealing with, let's say 350 degree flue temps. You would have a dew point that would be about 126 degrees roughly. However, if you were dealing with an appliance that was, let's say, a condensing type furnace, that you could have a stack temp that might be 95 or 100 and some degrees with the same amount of excess air, and your dew point would actually be lower than that, because the air would be so saturated is really what it comes down to. So it's really important for us to understand that dew points are really important to allow us to understand the materials, the issues that are going to have, and the importance of understanding how that impacts condensation. It's really a matter of dew point in our applications. So let's take a look at this. So one of the questions that I have is, what can happen on a cold start, and what do we add to our flue gases after they leave that furnace to lower that dew point? Well, that's really where our dilution air is coming into that application. And so in any type of a system where there is a draft hood, they're going to draw in dilution air to try to lower that. So that's one of the things that really has a big impact on that. Now, the other thing obviously that I want to also deal with is this dilution air, which, let's say that it's at room air of 70 degrees. Well, if that room air is at 70 degrees, it's also lowering down that air in the vent. So you might have a diluted sample to some extent. But because that dilution air is not, it's super dry, it's not saturated, there's so little moisture in it, it tends to dilute the sample of the flue gases within the vent pipe. And the resulting is that you end up with a substantially lower dew point, and that's what we need to have. That's what we really have to have. So, so let's take a look at this next thing. So, what exactly happens with something called wet time? And to some extent, when we have a problem with a system with wet time, what they're referring to is it's really the duration of when your vent wall temperatures will be below that dew point. All of those vent gases, or a high percentage of the vent gases that make contact with that vent pipe, if that vent temperature is equal to or lower than the dew point, you're going to get condensation, and that's really what is considered as a wet time. Now, that is essentially you're really going to see it on cold startups is the biggest thing. So what is the maximum amount of time that is for wet time? Well, the normal amount of time that you would hope that any vent system could be able to pull out of a wet time is roughly 2 minutes. Now, that's what you'd like to see. If there are going to be applications where that system could potentially run and never come out of that. But this is where your wet time is so critical to the type of vent system that you're using. If you're venting into a masonry chimney, it's almost impossible to ever come up with enough heat on a current appliance that would allow you to do it, unless you can sustain enough run time. Boilers, some of the boilers can get away with it, provided that that the chimney is not too big, and provided that they get sufficient run time. But I put a note on your runtime being critical. The longer I can make those furnaces run, the less likely I'm going to have problems with condensation. So that's really a very, very significant. All right, I put up a couple of images here. This one is something from the American Gas Association that was in a code book. And it talked a little bit about the duration or the time in seconds and compare that to the temperature in the vent system. And this particular line here, this one deals with the vent wall temp. This one here up on top deals with the average temperature. And on the bottom on here, you'll notice that this is essentially the portion where this represents the dew point. Now, it isn't until you reach that point right there where you'll see the wet time where your dew point is no longer going to be an issue at that point. So the number of seconds that it took from 0 all the way up to that point is really the amount of time that it's taking for this one. And this one here is typically dealing with a normal, like a draft hood type of appliance. Now, the other thing that I wanted to point out, and these are called draft hoods. The other thing I want to point out is the fact that you might have noticed that the temperature started to decrease. The dew point temperature got lower and lower and lower as it went along. And the point that I want to make here is that as the unit runs longer and longer and longer, the air, there's more and more dilution air as the draft increases. And that is going to cause that to drop a little bit. It's not significant, but it's just enough to make note of. It's part of their testing. So let's take a look at the next one. Now, in this particular application you're looking at, this is considered as a fan-assisted appliance. Now, I put a couple of images down in the bottom here of fan-assisted appliances, of furnaces that are using a fan. Now, these do not include or don't have any type of dilution air. And that's the one big thing to remember. So the wet time is going to be, it's going to actually go quite a bit longer. This is right here. If you look at this image based on the unit that they tested, you can see that we're in excess of 200. So we might be at 250 seconds of time. That's a fair amount of time that there's going to be condensation in the system. Now, I'm not privy to any of the additional types of statistics as far as what type of vent system, how did they run their test, did they do anything different as far as, is this with a B vent, is this with a chimney, anything like that. So those are, again, very significant issues that we have to deal with, but you can see the wet time is much longer. This has been an issue This has been a problem, this wet time for fan-assisted appliances. It's been an issue since day one, which really makes the sizing and the application of the vent system so much more critical, and I think that's the point I'm trying to make here. So what I have is this, as I've got since an induced draft does not have any dilution air, what problems does this create? Well, the higher dew point temperature in the gases without the dilution air means that you're going to condense a lot sooner. So the question I ask you is, how does an oversized vent system or an oversized furnace, affect the flue temperature and why? And the way that I have kind of looked at this is the reduced flue temps, because it's a little bit higher efficiency system, you don't have the dilution air. If the unit is short cycling, it never really heats up the flue. So you really never get a chance to, on an oversized furnace, you really never get a chance. The unit runs, it heats up the building super fast, it shuts off. You never really got a chance to sustain any types of temperatures. So again, the runtime has been completely created a problem with this. What are some of the ways to prevent condensation? So let's take a look at the first thing I would say is your sizing of the furnace vent system properly. You don't want to oversize that. You don't even want to oversize the furnace if you can help it. So the sizing, the load calc, those are going to be really critical. making sure your firing rate is appropriate. So check and adjust that firing rate. How do you do that? Well, make sure that you're getting your BTU input appropriate to that furnace. Now, for a two-stage furnace, this would be, it's important, but for a two-stage furnace that you're running it on low fire, it would even be a bigger issue. So that's a little bit of a problem. Checking and adjusting your temperature rise. So this is where your fan speed comes into play. So maybe you have to make sure you have your fan speed adjusted accordingly or appropriately. And these are, again, I have to speak in terms of new and old. So an older application, these are things that you'd kind of expect to have happen, and you hope you can correct them on these service calls. And then, of course, you might have a cycle rate adjustment on a thermostat. That could maybe help you a little bit. So thermostats, all thermostats now either have an anticipator or they'll have a cycle rate adjustment that will allow you to manipulate the time where the furnace kicks on and off. And you can make that bigger or smaller depending on the unit. So the bigger the cycle rate, or I should say the longer the runtime, your cycle rate would be slightly lower. All right, so let's take a look at this next one. So the first thing I'd like to deal with is we have two main furnace types for category, or two main vent systems for category 1 appliances. So the first one that we have on the left here is a typical cutaway of a masonry system, masonry chimney, and the one on the right is a metal vent system. Maybe that, you know, could be a B vent, could be BW, anything like those of that. It could be an L, number of different applications. So let's take a look at some of the parts and pieces here. So on this particular drawing that I'm looking at, I want to point out a couple of things. So on a masonry chimney system, you have a clay liner or clay tile liner. You've got brick around the outside of that. There's going to be mortar in between those joints. The picture here is not showing it, but there has to be an air gap that would be in between this fire clay tile liner and the brickwork. And they'll use actually a tie that will tie at the joints, at the mortar joints, they will tie the fire liner directly to the brick. So those are the things that will typically happen on these. Now, on the picture up on the top here, we're looking at a vent connector. And that vent connector, exactly what that vent connector is, it's really the portion of that vent system that ties directly from the appliance outlet connection going into the main vent of the system. So vent connectors are going to be used in any type of a vent system, whether it's masonry or whether it's a metal vent. So what's the problem with these masonry chimneys? So let's take a look at this a little more. So obviously the venting process is somewhat delayed, and that's a little bit of an issue. Now the image that I'm looking at here, we're showing a furnace that's venting into this masonry chimney. The tile liner is really cold and it's well below the dew point. So we're going to run into a lot of heat loss in this masonry liner. And there are systems, by the way, some masonry chimneys that have no liner in them at all. Now that's a bad design, but you can run into older homes where you will actually have no chimney liner whatsoever in there. And that's where you may see that as an opportunity to maybe add a liner. And they make metal liners, flexible liners that can be brought down the chimney and they could, they make them that are stainless steel, they make them that are aluminum. There's other applications, but you definitely want to be careful and take a look at that. The mass of a masonry chimney is a real problem on any type of lower efficiency appliance or any type of higher efficiency appliance where you're looking at the amount of heat loss that's in there. The image to the right on here, this particular one, you can see that we're showing a double wall B vent, and on this B vent we're only losing maybe 90 BTUs of heat that would go to that chimney liner to warm it up from 0 to 120. Substantially different compared to the other systems. So, what problems does this cause? And obviously the reason why I'm telling you about this is because condensation is a real issue, and also it creates more spillage. if you can't create the heat, if you don't have the heat to warm the vent system up, you're going to have a hard time getting the systems to want to draft and vent properly. So it creates more spillage out of the vent system, certainly on startup. So the huge advantage of a double wall vent system is it heats up so much faster, and that's the beauty of that. So on this image here, I have a B vent system, and I just wanted to point out a couple of things. This, you can see all the selection of, there's pipe here, different lengths that you can get. There's T's, there's elbows, a number of different types of accessories that we see. So let's talk a little bit about a B vent. What's critical about a B vent? A B vent system has an inner aluminum pipe, so the inner side of this is completely aluminum. And it's, as you know, aluminum heats up really fast, but it also cools down fairly fast. It's really, really low mass. The outer layer, in between the inner layer and the air gap that's shown in here, there's an air space that's in here. This is all air in here, and then the outer jacket is it's a galvanized steel outer pipe that they normally have. And that's fairly normal. The locking system. Now the locking system could either be by tabs that you assemble them or join them, or it could be some sort of a twisting locking system. So, but there has to be some sort of a mechanism in there that is used to assemble them so the pipes don't come apart once you push them together. You don't use screws in these systems. That is really recommended not to ever use that, simply because they're concerned about if you drive screws into a B vent, there's going to be some condensation that will eventually damage those screws and they'll fall out, and then they're a little bit worried about. But any locking system, they don't come apart that easy unless you're unless you're twisting them or changing them or doing something related to that. So let's take a look at this next image. So how much heat loss from the vent system to the surrounding space is reduced when you're using that double wall system versus a single wall pipe? Now, a double wall system, it's really, really, really low. You don't lose a lot of heat out of a double wall system in most systems, so your probability of condensation being a real problem is much, much lower. But in a single wall system, it is substantial enough especially when you don't have an excessive amount of heat due to the venting. So we really try to minimize the use of single wall pipe as much as we possibly can. The amount of heat loss is really about double for a single wall pipe compared to a double wall pipe. So that's something that we have to consider. So it's one of the reasons why we try to minimize the amount of use of single wall pipes, and maybe we only use them for vent connectors in terms of connecting the furnace to the main vent. That would be your best bet to do that. But if you can use the double wall as far as you can, that's really your best chance to get a vent system to correctly work. So I wanted to show a couple of examples here of single wall vent systems. Now, in this example, we're using a single wall vent. The furnace is not running. The vent, the vent is sized for max capacity of these units. So I'm looking at a water heater that's over here. I've got a furnace over here. Notice again, the furnace is not running. So the vent temperatures that are coming out of this water heater are about 355 degrees as our flue temp. That number could be up or down a little bit depending on the efficiency of your water heater. So by the time we get up to the very top of this vent system, with the amount of heat loss, I'm well below my dew point. Condensation is almost guaranteed, and in this situation, it's probably either going to run right back into that furnace. So that's a little bit of a problem. This is not really that typical. That's one of the reasons, again, why we would definitely not want to use this particular single wall pipe if at all possible. Condensation is pretty much all but guaranteed. Now let's change this to use a double wall system. Now in this system, we're looking at a furnace and water heater that's running. Again, the furnace is not running, the water heater is running, so we're keeping the same as the previous system. 355 degrees. By the time I get out to the top of this vent system, I might be down to 195 degrees. Now in that case, that may seem like a lot of heat loss. However, we're still well above the dew point. So condensation is really very minimal, and it's really probably only on the startup that it becomes a problem. The minimal amount that would happen during the initial startup is really it's really quite minor as a general rule. So condensation, as you can see, is really quite unlikely. So let's take a look at this. So what are some of the disadvantages of my single wall pipe? So a few of them that I put down in here. You know, heat loss to the surrounding area is definitely higher. You're going to have a lower average flue gas temp. The draft that you're going to be getting, that's what we're trying to get, is drafting. That's going to be much lower because I lost so much heat, and it's much more prone to condensing. So what about B vent? What are advantages of a double wall B vent? A lot less heat loss. You maintain your higher temps. You have higher pressures as far as your negative static drafting is much better, and it's a lot less likely to condense. So those are all good things. You try to use a B vent as much as you can when you're venting these types of appliances. So good opportunities. So let's take a look at it. So what's the main problem with an undersized vent pipe? Well, the first thing I would identify in this application, I'm looking at a furnace. Maybe you've got a more restricted flow out of the vent system. The other issue is maybe flue gases that are leaking or spilling out of the furnace because they don't want to go up the vent system. That can be a real problem. So those are things that we don't want to do that if we can help it. What about a too large of a vent system? Well, some of you might remember from our lab, we have one of our vent systems that's really, really large. And what happens is we run into a problem where either we don't get good drafting, we have condensation that leaks back down into the vent system. There are some issues. So in a situation like our lab, we have that issue simply because of the problems that we could run one furnace or we could run a whole bunch of different furnaces. So it's not the best ideal application. So, it's really a big problem that we have to deal with. So condensation is certainly going to be much more likely to have happen. All right, I wanted to also look at, what are some applications where we use these field installed power vent systems and how do they work for a natural draft furnace or a boiler? So in the image to the left, I want to just show you a simplified version, but on the exterior of your building, now this could be on the outside on the sidewall. You could easily also put something like this on the roof if it were coming out through the roof system. That's also another possibility. They make them for both applications. You also happen to have a barometric damper that is that's shown on the far left side in this picture. Now that barometric damper is really more used to fine-tune the amount of negative pressure that exists at the outlet of your furnace right here. Okay, so that's the reason for that. So if this draws too much gas out of the system, too much vent gases out of the system, the barometric damper will make up the difference, and it'll kind of dilute those products. So that's really kind of the gist of what they're doing. On the picture on the far left side, I also pointed out another application. This one is showing what looks like it could be a gas or it could be an oil-fired system, but we're showing a power venter coming off the side of the building. There's going to be some the vents, your vent gases are going to be pulled out through here, make its way all the way here, and this will make up the difference, however you fine tune that. So that has to be adjusted. So neat little systems that they make. So what do they do? How do they work? So a power venter, we're using a motorized blower, essentially is pulling those vent products out. The power venter, we have to interlock it to the appliance to make sure that we have draft before we're going to let the burners be activated. So that's kind of an important characteristic of it. Your draft motor, we would install it either in this case we're showing it as a horizontal run. but they do make them where they will be in a vertical run. Your piping, your damper, your motor, termination must all be sized properly. I've even seen these used in applications where they will undersize the vent system to save money, and they'll use this little power venter. The power venter will ensure that you will have draft in the undersized system if they size it correctly. But again, you really have to engineer these correctly. And then of course, the motor turns on, we make the amount of necessary draft, we draw dilution air, and we get things to work right. So it's a pretty neat little system. So why would I want to use one of these? Why would I want to use something like this to do it? So it could be, maybe this, your new efficient system absorbs so much more heat in the vent, or in the heat exchanger we produce, lower flue temps. It's going to ensure that I have proper draft. That might be one way. If it's I could have a problem where I just can't consistently get the appliance to draft correctly, and I'm constantly running into problems where I may be having limits and safeties that are causing failures. You could even see it where the customer might say, we keep having problems where you could have problems where my carbon monoxide detector is giving us issues. So, and again, those are all serious issues you have to address and try to deal with, but it is something that you can look at. And it certainly can be more economical. So let's say that I have an application where my chimney has failed, and I can get somebody to come in and repair the chimney, but that may be really, really expensive. So we may have to look at maybe some options and some alternatives. You could have a system where that was their design. They decided, we're going to do this as a sidewall application, and no problem. So it allows you to take something that is not designed necessarily to be a power vented application, but make it a power vented, and it's less expensive. And again, it can be a repair item that we could use on there that just can't get it to work right. All right, so let's take a look at a little recap on this. So of some of the considerations relative to our vent system. So we know that we're going to have a high volume of gases. So our flue gases can be fairly high. We can have, you burn a cubic foot of natural gas, you could have you could easily have 37.5 times the volume of gas if you consider the dilution air, the combustion air, the excess air, all those things. Your water vapor is an issue. You got to get your flue temps high enough in the systems that are going to allow you to prevent that condensation. So, your flue temps have a very significant factor. Your vents can be sized, too large, they can be too small. Those are some things that I have to make sure. So ultimately, I really want to appropriately size them and make sure that I'm doing my due diligence to make sure that I'm getting a system that's going to function correctly. Let's take a look at the recap of the venting materials and the characteristics for these vent systems. So a double wall vent system, as shown here, much lower heat loss. It primes a lot faster. Your venting action is a little bit better, considerably better than a single wall. You can use them in much tighter spaces because you don't need as much clearance from combustibles, and your condensation risk is much lower. Your single wall vent pipes, so much higher heat loss. The fire hazard due to the clearance from combustibles has to be much higher. In fact, it's generally 6 times the amount, so that's fairly significant. And then, of course, you're never going to be able to allow that to use. They will never let you use that in between floors or ceilings or anything like that. That's against any code that would exist. And then, of course, a masonry chimney. For any types of new appliances or newer, more efficient appliances, an unlined masonry chimney, even on older systems, I've seen systems where they were put in an older home that did not have a masonry or a metal liner, and those liners or those chimneys were starting to degrade and fall apart. It's a real problem that you have. You'll never ever heat that chimney up sufficiently to create sufficient draft, at least not thermally. You may be able to get it by current, but what they call torrential draft, but that would be the extent of it. But way too much of an issue on there. All right, make sure, I'm hoping you did this already, but if you haven't, complete the questions on natural draft vent basics. And you can proceed after this and you're completed, or when you're ready, you can proceed to lecture number 5.